Hello, my name is Mehraj Ahmed, and I'm here today with Shakeel Khan, and we will be presenting our tech talk on AI-driven drug discovery. So, a little bit of background, a biological background on our project is that we are studying the coronavirus, and the coronavirus essentially infects a cell, then hijacks its cellular machinery to produce copies of itself and viral proteins. And once it's produced enough of these viral proteins, that cell then explodes and these viral proteins are spread everywhere throughout the human body, and then this cycle repeats with a new cell. So essentially, viral proteins bind to cell receptors and infect them and damage them and clone themselves. So we are searching for a ligand which can neutralize this cycle by binding to a coronavirus protein and thus disabling its ability to bind to the human cell receptors. So here you can see a ligand, and here you can see the coronavirus protein. And if this ligand can bind to the coronavirus protein, then that coronavirus protein can no longer interact with human cells and damage the human body. So we utilized PAFNUSI, and PAFNUSI is an open source drug discovery convolutional neural network. It's been designed to determine the binding affinity between a protein and ligand. Binding affinity is the strength and stability of a bond, and we are searching for a very strong binding affinity to ensure that that ligand can completely neutralize that coronavirus protein. PAFNUSI receives the 3D structure of both the protein and ligand and transforms it into a 3D feature map of data. And then this data is run through internal mechanisms to determine how likely the protein and ligand are to bond and what the strength of the bond would be. And I will now pass it over to Shakeel Khan.
Hello everyone, my name is Shakeel. So we wanted to retrain the network with more data in order to obtain a better model that we can use for our COVID predictions. In order to do this, we needed to figure out a couple of things. First, we needed to figure out how we were going to obtain our data and from where. Second, we needed to find a way to clean it and prepare it for training. And then once we've trained the model, we needed to find a way to assess its performance. So for our approach, we decided to retrieve the data using some web scraping with Python. We also made a Python script that utilizes pandas to clean up the data and split it into the datasets required for training. And finally, we created a Jupyter notebook for analysis of the model after training.
This is our Python-driven web scraper, and we developed this web scraper with a Python framework known as Scrapy. Here you can see a list of all of the proteins that we were interested in investigating. Here you can see our first PDB spider. PDB is the database with which we extracted all of the 3D structures utilized in our training of the AI. So here, the purpose of this data is so essentially the AI can be both trained and validated because AIs require a lot of data to be trained very precisely. So here, the spider initializes the URL at the home page of the PDB database. It then stores the HTML source code of this website inside this response variable. This code then loops through the list found above here and will travel to the URL of each of these proteins, and it will pass the source code of that HTML into this right here. It calls this method, and this response stores the HTML code of that particular web page related to that protein. So here we create a new item known as the PDB scrape item, and here you can see the code for that. It just stores the file URL and the file name. So continuing, download is a new item. Link will contain the download link, which we extract via an XPath function. And then URL and name store the URLs of the download link and the name of the protein itself into individual variables. And then we will save these variables into our item container. We will then yield this item into our pipeline, and this pipeline will format the data slightly, and then it will continue to download the data. It'll handle all of the requests and processing needed in real time. So here in settings.py, you can see us enable downloader middlewares, enable item pipelines, and enable the file store, which will save the files of interest into the workspace or directory of our choice. A few things to keep in mind is that we had to adjust the download delay to make sure that the website wouldn't ban us for continually attempting to access their data. And we also enabled several middlewares to assist in our functionality. This PDB web scraper has done what it's been designed for, and it's been very useful in extracting large amounts of data from the Protein Data Bank database for our project.
Before I start talking about how the data cleanup script works, I'll give some background to the structure of the database. There are roughly 20,000 complexes that are split into three sets: the general, refined, and core sets. The further down the list you go, the higher quality the complexes become. The core set contains the highest quality complexes, only about 300, and will be used as a benchmark set. The database comes with an index file for each set, listing the complexes along with some other important info about them. Each complex has an associated protein and ligand file, which have info on the protein and the ligand for the complex respectively. So that's pretty much the database, and we're taking all that information to create our test, validation, and training sets. The test set is simply the core set. The validation set is composed of 1,000 randomly selected complexes from the refined set, and the training set is composed of the remaining complexes from the refined set and all the complexes within the general set. There should also be no overlap between these three sets. One of the issues with the database is that the index files contain some overlap. For example, the index file for the general set has entries for complexes that are within the refined set. Also, there are some entries within the index files that the database simply doesn't provide ligand and pocket files for. So we can't use those, and our script needs to be able to take all of this into account when creating the data sets. So at the top here, we have the general flow of the script. We start by opening up the index files. Then we remove any entries that we don't have the files for. We have an example of this right here with the general set. First, we get a list of the general complexes that we do have files on. Then we go through each entry in the index and we drop any that we don't have the files for. We do this for the refined and the core sets as well. Next, we remove the overlap from each set. We have an example of this down here, again with the general set. If there are any complexes within the general set that are also within the refined set, we drop it from the general set. The refined set at this point in time contains the core set as well. So, once this is done, we repeat the process with the refined set, removing any entries that are within the core set. Now that we've done all of the cleanup, we can go ahead and create the validation, training, and test sets. Here's an example with the test set. This is simply moving all the files for the complexes in the test set to another separate folder called test, so we have them all in one place. We also save some other important data that's needed by the neural network for training in a CSV file. And all of this code can be found at this link right here. So as we mentioned before, we created a Jupyter notebook to assess the performance of the model after training. It calculates a couple of performance metrics, specifically the root mean squared error and Pearson's correlation coefficient. It does this for the training, validation, and the test sets. RMSE essentially tells us how concentrated the data is around the regression line of the real and predicted values. The closer to zero this is, the better. Pearson's correlation coefficient measures the linear correlation between the real and predicted values. It ranges from -1 to +1, where -1 is complete negative linear correlation, 0 is no correlation, and +1 is complete linear correlation. In this case, the closer to +1, the better. The notebook also produces scatter plots and histograms to visually depict the performance of the model. So at the top here we have some code which calculates the performance metrics, and at the bottom we have the code that produces the graphs. Starting at the top, we have a method called calculate performance metrics that takes in the data sets. This is essentially a list containing the training, validation, and test sets, along with their respective real and predictive values of the binding affinity. We also pass in the name of each set. We then use the zip function in order to go through each set and calculate the RMSE and R values. We calculate the RMSE and R values using functions from scikit-learn, scipy, and numpy. So that's it for that. And down here, we have a method called drop predictions, which takes in the data sets, performance metrics, the name of the data sets, and a couple other parameters that are required for making the graphs. So we again just use the zip function here to go through each data set and create the graphs. We use Seaborn to create the initial graph, and we use a bit of matplotlib to do some fine-tuning and add the performance metrics. You can view the entire notebook and the graphs that you're about to see at this URL right here. So this is what the graphs look like. On the top here, we have the graphs for the model we trained, and on the bottom, we have the graphs for the original model that came with Pufnuzi. On the x-axis, we have the real affinities, and on the y-axis, we have the predicted affinities. This means that we are going to want the regression line created by the points to be pretty much linear. This means that the predictions are fairly accurate. We also put the values for RMSE and R on each graph. You may notice from the numbers here that our model has actually performed slightly worse than the original one, but we'll discuss that in a bit. So here's a quick summary of the environment we were using and the tech stack. So we use Python for everything, and we chose Anaconda as our package manager, mainly because it already has many of the packages we want, but it also has support for virtual environments right out of the box. As mentioned before, we use Jupyter Notebooks, and as for our IDEs, Mehraj used PyCharm a bit, but we all used VS Code. We actually set up a separate machine for training, mainly because we needed access to something fast, and we need to be able to access it easily, something with the same environment. So I threw together a machine, and we used SSH as well as Microsoft's remote development extension for VS Code in order to make working with the training machine a really easy process. So one of the things we learned is collaborating across different time zones. Mehraj was about 3 hours ahead of me, which is not much, but is still something we needed to keep in mind when it came to scheduling meetings and such. We decided to use Slack for communications because we could set up multiple channels for communication. It was also easy to share files and other items, and it was also easy to see what the time was for others. We also learned how to work on code together through Git and GitLab, which made sharing code overall much easier, and it made the whole process much more efficient. So for further work, some improvements we could make to the data cleanup script specifically is making it more user-friendly. There are some things you need to specify, for example, the version of the database being used, and this is currently done by setting parameters in the code. It's fairly straightforward, and we have documented the process on our GitHub, but our GitLab. But it would probably be much nicer to have a command line arguments instead. Additionally, we could optimize the data cleanup script a bit. As you may have noticed earlier, there were a lot of for loops, and we could probably just do away with those and use pure pandas methods to modify the data frames. We're pretty sure there is a way to do so, we just haven't had the time to look into it. Also, as mentioned before, the performance of the neural network wasn't what we were expecting after we did our training. It was slightly worse than the original one, pretty much comparable, but slightly worse. This was mainly because we just didn't have enough time. Training typically took 13 hours for us, so we could invest more time in this, tuning hyperparameters and such to come up with a better model. And that pretty much sums it up for the presentation. Here's our contact info if you would like to reach out to us, and we would like to give a big thanks to Code Labs for this amazing opportunity and our mentor Yang for her mentorship throughout the program. Thank you for watching, and we hope to hear from you in the future.